Last lecture we talked about the atomic spectra at the end. And there's one additional remark I'd like to make by going through this example. And that is, we have always assumed that, that if we have, for example, hydrogen atoms, that they are naturally in the ground state and not in some excited state. And if you have a gas at some temperature, then energy can be exchanged between the atoms, and some atoms can acquire more energies than others. And the question is this enough to actually excite some of the hydrogen atoms beyond the ground state? We are going to estimate the average kinetic energy of hydrogen atoms at room temperature. And we then explain from that estimate why all the hydrogen atoms are in the ground state at room temperature, and therefore they emit no light. To do that, we need to estimate the average kinetic energy. The average kinetic energy of an atomic gas is 3/2 times the Boltzmann constant times the temperature. And this is the value of the Boltzmann constant, 1.38 times 10 to the minus 23rd joule per Kelvin. And this is the 3/2. And then we multiply that with the temperature of this room, for example, which is approximately 300 Kelvin. And if we do that, then we get an energy of about 0.04 electron volts. And this energy is much, much smaller than the first excitation that we can excite, which was on the order of 10 electron volts. In a previous example, we had calculated that it takes 10.2 electron volts to get to the first excited state. And so it would require many, many collisions of hydrogen atoms to build up an energy of 10.2 electron volts. And that is extremely unlikely. Therefore, hydrogen atoms will all be in the ground state as long as they're at room temperature. Of course, once you increase the temperature by large amounts, then this may no longer be true. For example, for hydrogen gas in the sun. Before we finish our discussion of quantum mechanics, there's one important ingredient that we didn't talk about yet, and that is the famous uncertainty principle. So you may recall that we talked about Gaussian beams when we talked about diffraction, meaning that we have a beam that has a cross-sectional intensity as a function of radius that looks like a Gaussian function, or this function here. So we can consider a beam as the position uncertainty of photons, because beams is a bunch of photons. And the position uncertainty of the photon at the waist is roughly W0 parameter divided by 2. And that is because we have this, this factor of 2 in here instead of a factor of 1/2. So we constrict photons at the waist. We know that photons at that point have a transverse position that is within this range of delta x, which is the waist divided by 2. We also know that the beam divergence angle for such Gaussian beams is given as lambda over pi times the waist. We can now calculate what is the transverse momentum uncertainty that we know about those photons. If the beam is diverging, we can no longer assume that all photons travel exactly in the same direction. And so if we multiply this equation with the momentum, then the product of momentum times divergent angle, that gives us the amount of momentum transverse to the propagation direction of the beam. If we now use that the momentum is the Planck constant divided by the wavelength, then the uncertainty in the transverse momentum, meaning the momentum times the beam divergence angle, is h divided by pi over w naught. H over pi is 2 times h bar. So in other words, the momentum uncertainty in the transverse direction is 2 times h bar divided by the waist. And if we then multiply the position uncertainty with the corresponding momentum uncertainty in the same transverse direction, then we get that the product of those two is h bar. This is actually just one example of an uncertainty relation. But in any particle and in any situation, the uncertainty in the momentum measurement and the position measurement is always at least h bar and usually bigger than h bar. Also for photons in a Gaussian beam, we can multiply this relation, the first factor with the speed of light, and we can divide the second factor by the speed of light to get the same answer, h bar. And therefore, we get c times delta px, which is the uncertainty in the energy of the photon, and delta x divided by c, which is the uncertainty in the timing of the photon. And so we get another uncertainty relation that the product of energy uncertainty and time uncertainty is also at least as big as h bar. And that is also true for all particles and for all situations. Now, there are philosophical implications to this. In quantum theory or quantum mechanics, it isn't just that an emphasis that measurements have uncertainties. That's a trivial fact. But that the quantities themselves are not defined or don't exist beyond that uncertainty, meaning that it makes no sense at all to talk about a momentum that is more precise than that given by the uncertainty relation in quantum mechanics. And that means that quantum theory is necessarily probabilistic, since it requires both momentum and position determination with infinite position to define an exact trajectory. Exact trajectories don't exist anymore in quantum mechanics. Instead, you can only define probabilities. The setup of the experiment decides how much uncertainty I have in momentum and how much I have in position. For example, my Gaussian beam, I can have a wide beam. Then I have a very imprecise determination of position, but I have a very precise determination of the transverse momentum. Since those things don't exist beyond that limit of uncertainty, the way I make my experiment actually defines the physical reality, such as the interpretation of quantum theory. Many scientists did not like this kind of interpretation. They believe that reality should have an existence independent of whether we measure it or not. Another strange consequence of the uncertainty relation is that since we have one between energy and time, that means that we can borrow some energy out of the vacuum, out of nothing, as long as we don't do it for very long. If I want to create, say, an electron and a positron out of nothing, then I need to borrow about 1 MeV per c square, that is the mass, or 1 MeV of energy. And I can do that for h bar over 1 MeV time without violating any physics principle. And that means that the vacuum is constantly fluctuating, meaning that virtual particles are pair-produced out of nothing and disappear again for brief periods of time. And you may think that it has no consequence, but there are actually measurements that measure such quantum fluctuations. It means that, say, I have a position uncertainty of 1 millimeter and a corresponding precise determination of momentum. It doesn't make sense of even talking about, in quantum theory, of even talking about a position that is more precise than this 1 millimeter. If I have my Gaussian beam, actually here's one, but I have my Gaussian beam, where this one is 1 millimeter in size, then there is no definition of position within that beam. That position is only defined up to the limit of the size of that beam.
Oh, so that's the uncertainty?
Yeah, this is the transverse uncertainty of the photons traveling in that beam. And I cannot, for this particular beam, I cannot talk about the position of a photon, whether it's here or here or here. It doesn't make sense in terms of quantum theory of even talking about whether the photon is here, here, or here. We can only say that it's inside the beam, and similarly, given that there is this spread in the directions, I cannot talk about the direction of the photon more precisely than what is given by that beam.
So first you have to define an uncertainty before talking about.
Yeah. Yes. Yeah. So that is the weird thing, that my experimental setup decides how precise it is. And of course, there are other uncertainty relations where some quantities don't exist at all. For example, in our double slit experiment, it doesn't. The difference between this slit and this slit doesn't exist at all. So the light can take this path, or it can take this path, and you cannot talk about whether it actually took this path or that path. But the paths themselves don't exist, only the summation of both exists.
So how can you locate an electron, like a photon, in that setup? Do you have to also define an uncertainty?
I'm sorry, say again?
To locate the photon?
Yeah, if you locate the photon, then you have changed the experiment. So, for example, you can shine. You can block one of those slits, and then you have located the photon. It has to go through the other one. But then you have changed the experiment, and your interference pattern will no longer be the same. There are no less than 8 different philosophical interpretations of how to deal with this weird aspect of quantum mechanics, including the classical interpretation that reality ought to be independent of measurement. However, we can calculate still with the uncertainty principle, or with quantum mechanics. If we assume that an electron now moves in a straight line with a constant speed of 1.1 times 10 to the 6 meters per second, and it has been measured with a precision of 0.10%, this speed, then the question is, what is the maximum precision with which the position could be simultaneously measured? To answer that, we first express that speed in terms of the speed of light, because it's more convenient. So this is actually 0.367% of the speed of light. And we know then what the momentum of the electron is, because we simply multiply the electron mass classically, not relativistically, with that velocity, and we get a momentum of 1.87 keV per c. Given that we know that this momentum is measured to 0.1% precision, so if I multiply this momentum with 0.01 or 0.1%, then I get that 2 pi times delta p is this times 2 pi, is this times 2 pi, or 11.77 electron volts per c. So now I have a momentum uncertainty, or 2 pi times the momentum uncertainty, and I can now get the position uncertainty by taking the Planck constant and divide it by 2 pi times delta p. And that gives me 1.24 electron volts micrometers divided by 11.77 electron volts, or position uncertainty of 0.11 micrometers. So that is 900 atomic diameters, so it's a relatively small distance, but for an electron it's actually quite a large distance, because electrons typically uncertain within an atomic diameter. So this is how you would calculate with the uncertainty principle. Let's look at a macroscopic example. Let's calculate the uncertainty in position imposed by the uncertainty principle on a 150-gram baseball thrown at 93 miles per hour with an uncertainty of plus minus 2 miles per hour. We can do it the same way. We get the momentum uncertainty, which is 2 miles per hour, or 0.9 meters per second times the mass of the baseball. And that gives us a momentum uncertainty of this value. We now get the position uncertainty, and this is Planck's constant divided by 2 pi by this momentum uncertainty. And we get 7.8 times 10 to the minus 34 meters. So if anybody gives the uncertainty principle as an excuse why you couldn't hit the ball, it's a very lame excuse, because this is a tremendously small number, even compared to the size of an atomic nucleus. And finally, let's look at the energy-time uncertainty relation. So in the 70s, a new particle was discovered called the J-psi meson, and it is measured with an energy with a mass of 3.1 GeV per c square. But that measurement has an intrinsic uncertainty of 63 keV per c square. And the question is, how long does this particle live? In other words, the assumption is that the reason why it has an intrinsic uncertainty built into its measurement of the mass is that it comes from its finite lifetime. So we know that the energy uncertainty is this 63 keV, now without the c square, because this is an energy uncertainty. If I multiply it with 2 pi, then I get 396 keV. And then the corresponding time uncertainty, delta t, is just h divided by 2 pi, the energy uncertainty, or multiplying with c, it's 1.24 electron volt micrometer divided by the 396 keV, or 3.13 nanometers. And if I want to express this as a time, then I need to divide by the speed of light, and I get about 10 to the minus 20 seconds. So the lifetime of this meson is 10 to the minus 20 seconds. It's very short-lived, and that is why it has an uncertainty in its energy or in its mass built in. The really last remark about quantum theory, there is actually, even though I emphasized that electrons and electromagnetic waves behave very, very similar to each other, there's one important difference other than the charge of the electron, and that is photons and other so-called bosons that are like it, they like to be part of the same wave. For example, you can make laser beams where all the photons travel in the same state. However, so they are kind of sociable. Electrons, on the other hand, they're called fermions, and other such particles, other fermions, they are not very sociable. In fact, not even two of them will ever be in the same state. So that means, in particular for the atom, that no two electrons can occupy the exact same atomic level with the same angular momentum and the same spin. And that means that if you have complex atoms other than the hydrogen atom, that all the electrons can't be sitting in the ground state, but they will first fill in the ground state and then the higher states and so on. And that is important in understanding chemistry. So let me now summarize quantum mechanics. So we started with Planck's hypothesis explaining the blackbody radiation spectrum. And the assumption was that molecular vibration energy is quantized in units of hf, where f is the frequency and h is Planck's constant. And from that, Einstein suggested a particle theory of light, where the particle of light is called the photon. It has energy hf and momentum h over lambda. And this not only explains Planck's hypothesis, but also the photoelectric effect, the Compton effect, and electron-positron pair production. Light therefore has a dual nature, since we had many experiments which demonstrate that light is a wave, meaning that dual nature means it's both a particle and a wave. To turn it around, de Broglie suggested that particles like the electron also have wave properties with the wavelength h over the momentum. This led to the development of the electron microscope. The principle of complementarity requires that understanding one particular particle or wave needs to take into account both aspects, the particle as well as the wave aspect. And that is true for either light or matter. The experimental setup decides if the wave or the particle nature is revealed. Lastly, the early scattering experiments revealed that for the structure of atom, that the positive charge of the atom is concentrated in a small nucleus, which is surrounded by a cloud of electrons. And the Bohr-Sommerfeld model of the atom has electrons orbiting the nucleus like a miniature solar system. Standing electron waves using the de Broglie wavelength of electrons explain why the energy and the angular momentum as well as the radius is quantized. The quantization condition for the energy level is like this, where this is the ionization energy of the hydrogen atom. And this model is able to explain the atomic line spectra. So now we will move further inside the atom into nuclear physics and radioactivity. As I just reminded you, Rutherford found out that most of the mass of the atom is concentrated in the nucleus, since the electrons don't contribute much to the total mass. And atomic physics is about the structure of the electron cloud surrounding the nucleus. And nuclear physics is about the structure of the nucleus itself. So this is what we will be talking about now. So as a matter of fact, the nucleus consists out of smaller particles. And those smaller particles are called nucleons. And they come in two varieties. One is called proton and the other one is called neutron. The proton is positively charged with one elementary charge, and the neutron is neutral. It has no charge at all. Therefore, the protons are responsible for the charge of the nucleus, and the neutrons do not contribute. Those nucleons, they also consist out of smaller things, and those smaller things are called quarks. So 3 quarks make up one nucleon. And there are 2 types of quarks, the up quark and the down quark. And the up quark has a charge of 2/3 times the elementary charge, and the down quark has a charge of -1/3 times the elementary charge. And therefore, the proton is made up out of 2 U's and 1 D, and therefore it has a total charge of plus the elementary charge. And the neutron is made up out of 2 down quarks and 1 up quark. And therefore it has no total charge. And both the nucleons as well as the quarks are fermions, just like the electron, and unlike the photon. We can describe the atomic nucleus by 2 numbers. The charge number Z identifies the element and gives us the number of protons. And the atomic mass number A identifies the actual nuclide. And the difference between A and Z gives us roughly the number of neutrons. So the actual unit of A is little u, and it is defined by the chemists as exactly 1/12 of the mass contained in a 12-6 carbon atom. And that is roughly 1.66 times 10 to the minus 27 kilograms. Isotopes have the same charge in the nucleus, but they have different values for A. So here's a table of those particles, the electron, the proton, the neutron, and just as an example, the hydrogen atom. And here it is given in kilograms, and here it is given in those atomic mass units. And here it is given as the energy per speed of light squared. And you will notice that the neutron is ever so slightly heavier than the proton. And the electron is much, much lighter than either proton or neutron. The density of the nucleus is very high. And one can estimate the density of the nucleus by measuring its size with scattering experiments, just like Rutherford's scattering experiments. Since A is roughly the number of nucleons, and that is true because one proton weighs about 1 atomic mass unit and one neutron weighs approximately 1 atomic mass unit. Since we can measure the size of the nucleus, one can find this experimental relation that the nucleus is roughly a sphere of radius r, where the cube of that radius is given by 1.2 Fermi cubed times the mass number A. And a Fermi is 10 to the minus 15 meters, or about 5 orders of magnitude smaller than the diameter of an atom. And this relation implies that the volume of the nucleus is proportional to A, meaning to the number of nucleons. And therefore, nucleons can be modeled as hard spheres that don't penetrate each other. So the largest natural nucleus has a mass number of 238, and that's uranium-238. And using this relation, we find out that it's about 6.2 times bigger than the nucleus of an hydrogen atom, which is, of course, just a single proton. Let's estimate the density of nuclear matter and compare it to that of normal solids or liquids. Normal solids or liquids have typically about 10 to the 3 or 4 kilograms per meter cubed. For nuclear matter, we know the mass of a proton, for example, and we can use this formula, which relates radius of the nuclear sphere to the mass number. And if you plug in mass number 1, and this is just the volume of a sphere, 4 pi over 3 times radius to the third power, then we get about 2.3 times 10 to the 17 kilograms per meter cubed. That's about 15 orders of magnitude or so above that of a regular liquid or solid. We can make this estimate in a different way also. We can simply say, well, if atoms sort of just butt against each other, and we know the size of an atom is typically 10 to the minus 10 meters or twice the Bohr radius, then since the size of a nucleus is typically 10 to the minus 15 meters, and we simply take the ratio of that to the third power to give us the volume, and that gives us also about 10 to the 15 orders of magnitude more than in a typical solid. Nuclear matter is very, very dense. So you may ask yourself, since we know that there are only protons and neutrons in the nucleus, and the protons are positively charged, how come the electrostatic repulsion between the protons doesn't blow the nucleus apart? What keeps it together? And the answer to that question is there's another force of nature that is distinct from electromagnetism, and it's called the strong force. It is an interaction similar to the electromagnetism, but not the same. And it's actually stronger than electromagnetism, in the same way as electromagnetism is stronger than gravity. And in electromagnetism, we have learned that there's one signed electric charge. The strong force, however, is more complicated, and it has 3 signed charges. And those are typically called colors. We call them red, green, and blue, those charges of the strong force. And the protons and the neutrons, they are not just made out of quarks, which have an electric charge, but those quarks also have a color. There are red quarks, green quarks, and blue quarks. And actually, proton and neutron are made out of quarks, one of each color. So here's how this looks like. So we have the proton. It has, for example, red U quark and a green U quark and a blue down quark. And so it has the total electric charge of +1, and it has the total color of white, because red, green, and blue is color neutral or white. And when I talk about those colors, this is an analogy. It is not the same as the colors that we see with our eyes. It is simply a reflection of the rules how to calculate with those color charges. For the neutron, there are also 3 colors, so both neutron and proton are color neutral. So in principle, the strong interaction doesn't have anything to say about proton and neutron, just about the quarks inside. However, it's not a static system, the proton and the neutron. And there are fluctuating color dipoles or multipoles. So sometimes the bottom part is colored green, or sometimes it's colored red, or sometimes it's colored blue. And it always changes for both proton and neutron. But if you sum up the corresponding interactions between proton and neutron, then you come up with an overall attraction. And that is somewhat similar to the case of atoms attracting each other. Atoms are electrically neutral, but there are so-called van der Waals attractive forces between atoms or between molecules due to fluctuating electric dipoles. Such forces are always short range in nature. So they don't propagate out to infinity like electromagnetism would. They only work at short distances. And they are typically quite weak. The van der Waals force is much weaker than the typical electrostatic force. However, since this... Oh, sorry, yes?
In the previous slide, what's the difference between the colors? Is it just the quantity of the charge? Or
No, they are different in nature. So they are different qualities. So a red charge, you cannot express a green charge with red charges. It's a different thing. Yeah, either one can be positive or negative. You can have a positive red or you can have a negative red, and you can have a positive blue or you can have a negative blue.
So is it the quantity of charge in each particle that causes
Yeah, unlike for the electric charge where it was enough to give one number for the electric charge, for the color charge you need to give 3 numbers. How much red, how much green, and how much blue. Each one is fundamental, so you cannot express it with the others. As I said, the van der Waals force is weak, and therefore the nuclear force is weak compared to the full-blown strong force. However, even that small residual effect of the strong force is still enough to overpower electromagnetism. And so if we look at the potential energy of, say, a proton and a neutron as a function of distance between them, so this is potential energy, this is distance, then at a very short distance, this attractive force is overpowering electromagnetism, sort of forms this well. And then once you get beyond the radius where that force is effective, then you get the normal Coulomb repulsion between the nucleons. So if we look at the combination of those, we see a potential barrier, which is this part here, and a potential energy well. And so once nucleons are bound together in a nucleus, they're sitting down in this well. And as long as they don't keep above this barrier, they will stay contained. The binding energy of the nucleus is quite large. One can calculate the mass that is equivalent to that binding energy. So if we have a binding energy E bond, we can calculate a mass, a corresponding mass M bond, which is simply the energy divided by the speed of light square. This binding energy is so large that it cannot be neglected when calculating the mass of a nucleus. So the total mass of a stable nucleus is always less than the sum of the nucleons. And one can even use a stability criterion, meaning the more binding energy you have per nucleon, or the more mass loss you have per nucleon, the more stable the nucleus is. And a typical value for this binding energy per nucleon is 8 MeV. And you see it varies as you go across the different nuclides. Here we plot the mass number, or the number of nucleons on the horizontal axis, and this binding energy per nucleon. And it peaks with iron, and then it has various peaks and valleys on the way there. So instead of calculating this example, I want to finish here with an experiment. And that is to demonstrate that not all nucleuses remain intact forever. So it was discovered that some nuclei are unstable and disintegrate after some time. And there are 3 different types of such disintegrations, which are called alpha, beta, and gamma. So this one is an alpha emitter. And here I have a particle detector, a small one. And let me insert this in here. Before I fully insert it, let's first count the background rate. So such radioactive events happen naturally in the environment all the time. So let's just do a count without inserting the unstable nuclei. And we get about 9 counts. Nine counts per 6 seconds. And if I insert these unstable nuclei in there, and I count again, then each count is one disintegrating nucleus. So we have about 3,600 counts in 6 seconds, or about 60 counts per second, also called 60 becquerel. So this is an alpha emitter, and alpha emitters, the resulting radiation, and we will talk about that next time, what that radiation is very easily shielded even by a piece of paper. So if I insert this piece of paper in here, then we will already see a reduction in the count rate. So with the paper, we have about 60 counts per 6 seconds, or about 10 becquerel. Sorry, this was 600, not 60. So a simple sheet of paper can shield you from this radioactive element. So that means that your skin is a good protection for it. And the only danger such radioactive elements pose is if you get them inside your body. So this is a different type of radioactive element, and it disintegrates in different ways. So a piece of paper is not going to shield this one. So first of all, the activity is something like 360 counts. And if I put a sheet of paper in there now, then there's not much difference. Slightly less, but not very much difference. However, if we put a metal sheet on top of it, aluminum, then now the count is reduced. Now it's only about 60 counts. So lastly, a third element, a third type of nuclear disintegration. This is called beta, and this one is called gamma. Let's first count the activity without any shielding. And it's about 100 counts. And putting my metal shield on top of it, doesn't make much difference. So gamma radiation will get punched through that metal shield, and it actually requires heavy lead shielding to shield it. Even that one doesn't shield it completely. Still get about half the counts. Can try and put more lead shielding on top of it, if I can still squeeze it in between. So some of it is still going through. So alpha radiation, when it hits your body, does the most damage, but it's easily shielded. Beta radiation is more penetrating, but it does less damage in your body. Gamma radiation does the least amount of damage, but it's very difficult to shield, and it typically requires very dense metal bricks to shield it. So thank you for your attention.